All right, hello everyone. We're going to be talking about section 4.3 today, which is going to be about logarithmic functions. So first we're going to talk about common logarithms. Just an idea to have is that logarithms are simply a new language for old ideas. And this just means that logarithms are just a special case for exponents. It's another way that we can write out exponents. So we have the definition of the common base 10 logarithm. So we have y is equal to log x, which means 10 to the y power is equal to x. So whenever we see y equals log something or something along those lines, and it doesn't have a defined base or subscript after the log, we're always going to assume that that log means log base 10, which that just means that we have that second equation here with our 10 to the y power is equal to x. So let's start with example 1, and this is going to be checkpoints 1 and 2 combined. So we have our very first part here, which is problem A. We have log 100. So if we rewrite this, since we're assuming, since it has an undefined base, that it's going to be log base 10. So let's just rewrite this so we can rewrite as y is equal to log base 10 of 100. And so now what this means is that we have this y equals log base 10 of 100, which is going to be x. So we know that this is equivalent to 10 to the y power is equal to x. So we know that 10, I'm gonna write it right under here, 10 to the y power is going to be equal to 100. So we can just take a moment to deduce what y might be. What do we know? If we use an exponent on 10, we'll create 100. And we should get y is equal to 2, since 10 squared, or 10 times 10, is going to be 100. So now we can move on here to part B. We have log of 1,000. So let's rewrite this again and just write it out. We have y is equal to log base 10 of 1,000. So we know, like last problem, that this means that 10 to the y power is going to be equal to 1,000. So we can take a moment and deduce what exponent of 10 will create 1,000. And we get that y to the third, or y equals 3, so 10 to the third power will give us 1,000. All right, and part C here, so we'll rewrite this. Y is equal to log base 10 of 0.1. So now we have a decimal here. But we know that 0.1, we can rewrite this. So we can say, rewrite as y is equal to log base 10. And 0.1 is the same thing as saying 1 over 10. So we know that 10 to the y power is going to give us 1 over 10. So now we can deduce what exponent y will create 1 over 10. Well, we know that anything to the negative 1 power will just create a fraction of 1 over whatever our base was. So we know that y is going to be negative 1. So 10 to the negative 1 power will give us 1 over 10. All right, so now we can move on to part D. So now we have log of 27. So since we have a log with an undefined base, we know this is log base 10. So even when we rewrite this, we know y equals log base 10 of 27. It's pretty easy to assume that 10 to any power is really not going to be evenly equal to 27. So we still rewrite this. We say 10 to the y power is equal to 27. And we can start to make an assumption. So 27 we know is greater than 10, but it's also less than 100. So we can assume that whatever our y is, it's probably going to be between the numbers of 2 and 3. And since 27 is much closer to 10 than it is to 100, it's probably a low value of 2, something around 2.1 or 2.2 or 2.3, something much smaller than 3 itself. So you can actually use a calculator in order to calculate this, and you should be able to get y is equal to, I realize I misspoke. So I said between 2 and 3, and it should have been between 1 and 2. So 10 to the first power and 10 to the second power, which means 10 and 100, not 2 and 3. So it should be closer to 1 than it is to 2. So we can use a calculator in order to calculate this, and we should get 1.43, which is much closer to 1 than it is to 2. All right, so part E here, we have log of 1089. So we know we can rewrite this. We get y is equal to log base 10 of 1089. And so we know that 10 to the y power is going to give us 1089. And in this case, we see it's greater than 1,000, but less than 10,000, which would be 10 to the third power and 10 to the fourth power. So we know it's going to land somewhere between 3 and 4. And once again, we see it's much closer to 1,000 than it is to 10,000. So we can assume it's probably going to be a lower value of 3. So we can use a calculator. And if you did, you should have gotten y equals 3.04. All right, and last part, we have part F, which is log of 0.00426. So we want to rewrite this as y is equal to log base 10 of 0.00426. And since we have a much smaller number in this case, it can be kind of hard to tell what numbers it is between. But we do know that this would be in between y is equal to -2 or -3. This number lies in between those two values. But either way, we'll use a calculator in order to calculate this. And we know we should get y is equal to -2.37. All right, so that's how we find common logarithms. That just means logarithms with base 10. And anytime you see just a log with an undefined base, we can automatically assume that that base is going to be 10. Also, if you ever use a calculator and you just type log and you don't specify a base, your calculator will also assume that it is log base 10. So if you ever have a different base, remember to define a base, or else you'll be stuck with log base 10. All right, so we also have here that logarithms of negative numbers and 0 are not defined. This means that logarithms, they can equal a negative number or 0. So y can be a negative number or 0, but x can never be negative or 0. So you can never take logarithm of 0 or logarithm of a negative number. And that is how we say it in terms like this. Whenever we see y is equal to log x, we usually say y is equal to log of x or logarithm of x. Log is just a short term of saying logarithm. All right, so now we can move on. We have natural logarithms. So common logarithms are still used and they're still useful, but natural logarithms are the most used and they prove themselves to be more useful in certain cases. So we have the definition of the natural logarithm. So it has the base e. So in our last sections, we talked about the number e, which is around 2.718. So it is a numeric value, but it is an irrational number. So we have logarithm-based e, which we will signify as ln. So we'll say y is equal to ln of x, which means that e to the y power is equal to x. So it's the same general idea that we just went over, and now instead of the base being 10, we now have a base e, and it's written a little differently. So we have example 2 here, which is also checkpoint 3, and we want to find the following values. So we have the natural log of 6.1 for our part A here. So we want to rewrite this just as we did before. So we'll get that y is equal to log base e of 6.1, or we can just write ln of 6.1. Your calculator should have a function that's just listed as ln, so you shouldn't have to specify log base e. Now, since we know that this is e to the y power is going to be equal to 6.1, we can use a calculator to calculate what this might be. And we get that y is equal to 1.81. Now for part B, we can do the same thing as before. So we know that y equals the natural log of 20. So e to the y power is going to be equal to 20. And by using our calculator, we should be able to find that y is equal to 2.996, and we can assume that y is around 3. So we know that the number 20 is almost e to the third power, just a little off. So for part C, we have the natural log of 0.8. So we can rewrite this to give it a y. And we know e to the y power is going to be equal to 0.8. And we can use our calculator in order to solve this, which you should get negative 0.22. This is another one of those examples. See, our x values can't be 0 or negative, but our y value can still be negative or 0 in these cases. All right, now on to part D, we have the natural log of 0.1. So we take y is equal to the natural log of 0.1. So this means that e to the y power is going to be equal to 0.1. And we can use our calculator to calculate this. And we should get y is equal to negative 2.3. All right, and lastly, we have here for part E, we have the natural log of our exponent e to the 8th power. So this means that y is equal to the natural log of e to the 8th power. And we're about to see something kind of funny happen. So we get e to the y power is equal to e to the 8th power. And it's pretty obvious what y is going to be, because e to the 8th will have to be equal to e to the 8th. So we know that y is equal to 8. An important thing to notice that the natural log, since the natural log has log base e, that whenever you have an e to an exponent as the x value, that the natural log and e will cancel each other out essentially. So you'll just be left with whatever that exponent was. So in our case, we had the natural log of e to the 8th power. Well, our answer is just going to be 8. Y is equal to 8. If it were the natural log of e to the 4th power, our answer would just be 4. And if our problem was the natural log of e to the x squared, we would just have x squared. So they essentially cancel each other out, and you're just left with whatever was in the exponent. All right, so now some other logarithms we have. The procedure we've been using for common and natural logarithms, they can be used with any positive number that doesn't equal 1. So this means that if we had a theoretical constant, a, that just means that a will have to be greater than 0, but it cannot be equal to 1. So anywhere in between those. As the base, as opposed to 10 or e. So you can have this value of a as a base as long as it's greater than 0 and not equal to 1. You can have it equal to 1. The only thing would that be 1 to any exponent is always going to be 1. So the only answer for log base 1 will have to be 1. So that's why we don't use 1, but anything greater than 0. So we have our definition of logarithms to the base a, our constant a. So we have y is equal to log base a of x, which means that a to the y value is going to be equal to x. And we want to frame our logic the same way as before. So we have our logarithm for form. We'll have y, which is our exponent, is equal to the log base a. So a is our base of x. And in our exponential form, which we'll use our base, which is a, to the exponent y, is equal to x. So now for example 3, which are checkpoints 4 and 5, or parts of 4 and 5. So we'll write for a and b, we'll write the logarithm form, and then for parts c and d, we'll write the exponential form. So in part a, we're given our exponential form, which is 5/3 is equal to 125. So what we want to do is write it back in our logarithm form. So we want it in this form instead of this form. So we want this form here. We want y is equal to log base a of x. And we see that our exponent is 3, which is equal to y. So we're going to start with 3. We'll say 3 is equal to log of our base. It looks like our base is 5, so we'll have log base 5 of x, which is 125. When you're writing these, it's really important to have your base really small so you don't accidentally confuse your base with being an undefined base and then maybe add it on to whatever your x value is. So just make sure that whatever your base is, it's written small and it's definitely below the logarithm. And then we have our x, which was 125. So we have taken our exponential form and rewritten it into our logarithm form. Now we have part B. So we have 8 to the 2/3 power is equal to 4. So we're going to do the same thing. So 2/3 is our exponent, which is y. So we'll start with that. So we'll say 2/3 is equal to the log of our base, which is 8. So log base 8 of x, which is 4. So now we know that 8 to the 2/3 is equal to 4, and that 2/3 is equal to log base 8 of 4. All right, so now we're going to write the exponential form for parts C and D. So it's already in logarithm form, and we're now just writing them as exponential form. So we can look at our problem. We have log base 3 of 1/9 is equal to -2. We have that 3 is our base, since that's our log of something. So log base 3, so we know that it's going to be 3 is our base. We know y is our exponent, so we have that our logarithm is equal to -2. -2 would be our y, so we can say log of -2 is equal to our x, which in this case is 1/9, and we know that that is what our logarithm form shows here. So we had -2 as y, 3 as our base, and then our x, which is 1/9. All right, then we have for part D, we have log base 16 of 4 is equal to 1/2. So we see our log base 16, so 16 will be our base, is equal to 1/2 or equal to y. So y is our exponent. So our exponent is 1/2. So we have 16 to the 1/2 power. And we see our x there is going to be 4. So we have 16 to the 1/2 power is equal to 4. All right, so now that we've learned a few different forms of logarithms, we have our natural log, our common log, and now we have just our other logarithms with different various bases. And we know our logarithm form and our exponential form. We're going to move on to the properties of logarithms. The logarithms have quite a few very important properties that will come up many times just throughout mathematics. So for our first part here, we have let x and a be any real positive numbers, and a can't be equal to 1, and r will be any real number. Then we have our 4 properties here. So if we have log base a, so a can be any real number, of 1 has to be equal to 0. And this is because we know anything to the 0 power, I don't know why that happened, to the 0 power has to be equal to 1. So if we're saying log base a of 1 is equal to 0, we know that 0 is our y, or our exponent, a is our base, and so 1 has to be our answer. And we have for part B here that log base a of a is equal to 1. And we know that because that means a to the first power has to be equal to a. So 1 is our exponent, we know a is our base, so if we have a to the first power, that's always just going to be a. Now we have log base a of a to the r power is equal to r. And that's because we know that if y is our exponent, and we have a as our base, r is our exponent, a to the r power, of course our answer has to be a to the r power. So that just means that r is any real number with our a base. Now we have a to the log base a of x is equal to x. So now this one's going to be a little bit more tricky. So we have y, which is log base a of x, since that was our exponent, is going to be equal to the log of our base of x. Our base is a, so we have log base a, and our x value in this case is x, so we know we have x. So we know that that checks out. All right, so now moving on, we have our product, quotient, and power properties. So we let x, y, and a be any positive real numbers with a not equal to 1, and then we're going to let r be any real number. So now we have first our product properties. So we have log base a of x times y can be separated into log base a of x plus log base a of y. And these can go either way. So you can draw arrows here. They go either way. So if you have log base a of x times y, you can separate it into log base a of x plus log base a of y. Or if you have log base a of x plus log base a of y, we could turn that into log base a of x times y. That's a mouthful. All right, so that property works in both directions, so we know that whenever we have one of those terms, we can change it to make it more simple either way. So now we're moving on to our quotient property. So very similar, it's just now instead of multiplication, we're working with division and subtraction instead of addition. This property also goes both ways. So if we have log base a of x divided by y, we can turn this into log base a of x minus log base a of y. Or other way around, if you have log base a of x minus log base a of y, you can turn that into log base a of x divided by y. This is another way to simplify our logarithms. Then finally, we have our power property. So if we have log base a of x to the r power, we can turn this into r times log base a of x. So this one's a little bit more confusing, but it also works in both directions. So if you have log base a of x to the r power, you can turn that into r times log base a of x, or if you have r times log base a of x, you can turn that into log base a of x to the r power. All right, now that we've learned some of our properties here of logarithms, we can try a few out. So for example 4 here, we're going to write each expression as the logarithm of a single number or expression. So we're going to use our properties to combine all of our logarithms into one logarithm of a number or expression. All right, so we're going to go from left to right in these cases. So we have for part A, log of 6 plus log of 8 minus log of 2. Now we have undefined bases, so we know that this means log base 10. And since they're all undefined, we can combine them all since they all have the same base. So we have log base 6 plus log of 6 plus log of 8 minus log of 2. And if we're working from left to right, we're going to start with the first two terms. So we have log of 6 plus log of 8. And we know from our property, this means that we can write this as log of 6 times 8. So let's write that. We have log of 6 times 8, and we're going to keep this log of 2 there, or minus log of 2. And we're going to simplify our log of 6 times 8 first. And if we do this, all we want to do is multiply 6 and 8. So this gives us a log of 48 minus log of 2. So now we've simplified our problem from having 3 log terms into having 2 log terms. And we want to simplify this as much as possible, remember. So we're going to do this one more time. So we have log of 48 minus log of 2, and this is our quotient property right here. So we're going to rewrite this as log of x divided by y, or 48 divided by 2. This is the same thing as saying log of 48 divided by 2. 48 divided by 2 is just going to give us log of 24. So our final answer will just be log of 24. You'll also see that sometimes I'll write parentheses around whatever we were taking the log of, and sometimes not. It doesn't matter. It's whatever your preference is, whether or not you would like parentheses there or otherwise. I usually have parentheses whenever there is a function happening, like multiplication or division in these cases. But just letting you know. For part B, we have 2 times the natural log of 5 minus 1/2 times the natural log of 25. So now we have a number being multiplied in front of our natural logs, which we know our natural logs are log base e, and they're both natural logs, so we can use our properties. And we have 2 times the natural log of 5, and we have 1/2 times the natural log of 25. And this looks pretty similar to one of our properties, which happens to be our power property. We see that since r, in this case 2 and 1/2, are being multiplied by our natural logs, we're going to switch this up and we're going to put them back in exponent form. So to do this, we're going to rewrite this as a natural log of 5 to the 2nd power minus the natural log of 25 to the 1/2 power. All right, so now we just want to simplify these terms. The natural log of 5 to the 2nd power, 5 times 5, is going to simplify to the natural log of 25 minus, and 25 to the 1/2 power is the same thing as saying square root of 25. So if we calculate this, 25 to the 1/2 power, or the square root of 25, is going to be the natural log of 5. And now we have one term minus another term, which looks awfully a lot like the quotient property. So we're going to use our quotient property to do this. And we're going to simplify this to be equal to the natural, keep writing h, the natural log of 25 divided by 5. Just like our quotient property there. And we know that 25 divided by 5 is going to simplify to 5, so we know that this is equal to the natural log of 5. So now we have simplified our expression, which in this case had 2 terms. We now simplified it just 1. All right, and so for part C, our very last part in example 4, we have the natural log of 3x plus 2 plus the natural log of x plus 4. So now we're not working with real numbers anymore. We're working with variables and expressions like how we said earlier. So we can still simplify this term, and we see that they're being added to each other, our natural logs here. And so we can say, okay, well, let's use the product property since we're adding these terms together. So this is going to turn into the natural log of 3x plus 2 times x plus 4. And you can feel free to leave it in this form unless maybe a question specifically asks you to simplify. And if it asks you to simplify it down to its smallest form, you can multiply those expressions together if you would like. And that should give you 3x squared plus 14x plus 8. So you can feel free to leave in the very first term we had here, since we have now simplified it down to just be one logarithm, or you can multiply those inner expressions if you would like. All right, and just a word of caution when using these properties. There is no property that allows you to simplify the logarithm of a sum or similarly a difference. So this means whether they're being subtracted or added or whatever. So we have an example. We have the natural log of 3x squared plus 14x plus 8. And this is not equal to the natural log of 3x squared plus the natural log of 14x plus the natural log of 8. So in cases like this, you cannot separate them. It only works if they're being multiplied. So we could separate it like that if we had the natural log of 3x squared times 14x times 8. We could separate it like that, but we can't since they're being added. So just remember that there is a difference and you cannot do that. It is a mistake that is seen constantly. Even when you get up into higher mathematics classes, it's still a mistake that is made a lot. So make sure to know the difference. All right, for example 5, which is also checkpoint 7 in your book, we're going to use properties of logs to rewrite and evaluate each expression given that log base 3 of 7 is going to be equal to, or about equal to, 1.77, and log base 3 of 5 is about equal to 1.46. So for part A, we have this log base 3 of 35, and we don't know what log base 3 of 35 is unless we use a calculator. But we know that 35 is equal to 7 times 5. So we're going to rewrite this. So we're going to say rewrite as log base 3 of 7 times 5. And now that we've rewritten it, we see that we have 7 times 5, or like our property had said before, x times y. So we're going to rewrite this as log base 3 of 7 plus log base 3 of 5. Now we know what log of base 3 of 7 is, and we know what log base 3 of 5 is. So we're just going to replace these values. And since log base 3 of 7 is about 1.77, we can say 1.77 plus log base 3 of 5, which is 1.46. 6. All right, now we can just add these up together to find out what log base 3 of 35 is. And we should get 3.23. All right, and we'll do the same thing for part B here. We have log base 3 of 7 divided by 5. Now we see that 7 is already being divided by 5 and it's not like a decimal or anything along those lines. So we can just rewrite it straight out into our expanded form using our property. So if we have log base 3 of 7 divided by 5, we know that this is equal to log base 3 of 7 minus log base 3 of 5. And now that we have these and we know our values, this is going to be 1.77 minus 1.46. And by subtracting these values, we will get 0.31. All right, and now for part C, we have log base 3 of 25. So similarly to part A, we don't know what log base 3 of 25 is unless we use a calculator, but we do know what log base 3 of 5 is. So we can rewrite this to be log base 3 of 5 times 5. Now, we also know that 25 is the same thing as saying 5 squared. So this is also log base 3 of 5 squared. And since we already used our product property, let's use our power property this time. So let's use this log base 3 of 5 to the second power. So now when we rewrite this, this is going to be equal to 2 times log base 3 of 5. And we know what log base 3 of 5 is. It's going to be about 1.46. So we'll do 2 times 1.46. And this is going to give us 2.92. That's point, not multiply. 2.92 is going to be our answer. So now we have used our product, our quotient, and our power properties now. And for part D, we're going to use some of those other properties. So for part D, we have log base 3 of 3. And if we notice, well, this looks a lot like log base A of A, which we know when we rewrite this in exponential form, this means that we have 3 to the y power is equal to 3. So we get that y has to be equal to 1. All right, so now we have log base 3 of 1. This is similar to one of the first properties we learned as well. When we rewrite this in our exponential form, we know that 3 to the y power is equal to 1, and we know that anything to the 0 power has to be equal to 1. So we know that in this case, y is equal to 0. All right, so now we've used some of our properties to rewrite and evaluate some expressions. And now we can move on to another way to calculate log base A of x is to use a change of base. And our change of base theorem is just telling us that for any positive numbers a and x, when a is not equal to 1, of log base A of x is equal to the natural log of x divided by the natural log of a. So this just means that if we have log base A of x, we can rewrite this and calculate it a different way, and so we can have the natural log of x divided by the natural log of a. So this just gives us another way to calculate our logarithms that may have, different bases. All right, to start with, we're going to do example 6. So we want to find log base 5 of 9. So we're going to use the change of base theorem with a equals 5 and x equals 9. So if we rewrite this, we're going to get our log base 5 of 9 is the same thing as saying the natural log of 9 divided by the natural log of 5. And now we get to use a calculator because we want to find out what the natural log of 9 is, and we want to find out what the natural log of 5 is. And if we use our calculator, we know that our natural log of 9 is going to be about 2.197, and our natural log of 5 is going to be about 1.609. So if we calculate that fraction, we'll end up with 1.365. Now, I strongly encourage you to pause the video for a quick second and go to a calculator and calculate what log base 5 of 9 actually is. All right, and if you have done that, we'll see that the actual value of log base 5 of 9 is going to be 1.365. It's about that value. So it's about 1.365. So now we see that our change of base theorem is accurate because it will give us the same value, or about the same value. All right, moving on to a much harder example. We have example 7 here, which is also example 10 in your book. I thought it was important to go over this example, especially since it is more complicated than what we have seen so far. So we have here is a natural science problem. So we have environmental scientists who study the diversity of species in an ecological community use the Shannon index to measure diversity. If there are k different species with n sub 1 individuals of species 1, n sub 2 of individuals of species 2, and so on, then the Shannon index H is defined as, and we get H is equal to capital N times the log base 2 of that capital N minus n sub 1 times log base 2 of n sub 1 plus n sub 2 times log base 2 of n sub 2 plus, and then we have our dot 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 to represent any species or our n sub value to represent the that certain species. We add all of those up until we reach our k amount of different species, which would be n sub k of log base 2 n sub k. And we see that that capital N is going to be our n sub 1 plus n sub 2 plus n sub 3 all the way up to our plus n sub k. And we see a study of the species of barn owls in a particular region typically yielded the following data. So we get that our species, which are going to be rats, mice, and birds, and our number of rats is 143, our number of mice is 1,405, and our number of birds is 452. And we want to find the index of diversity in this community. That was a mouthful. All right, so if we begin here, we see we have 3 different species. So let's just state some facts first. So we know that n is equal to n sub 1 plus n sub 2 plus n sub 3. We have 3 species in this case, so we know that there's only 3. And we know that n sub 1 is going to be rats. So our species 1. And we know that rats, our number of rats is 143. So our n sub 1 is equal to 143, and it's representing rats. Now we have n sub 2 is going to represent mice, and there's 1,405 mice. So we have n sub 2 is equal to 1,405. Then we have n sub 3, which is equal to birds, or representing birds, and that is equal to 452. So our capital N is going to be all these values combined. So if we add these, this means that capital N is 143 plus 1,405 plus 452. We take a moment and add all of these values together. We're going to get 2,000. So this means that capital N is equal to 2,000. All right. So now we've established what our capital N is, we've established what our n sub 1 is, what our n sub 2 is, and our n sub 3 is. So now we have our equation here, and I'm just going to rewrite it. We have h, let's do h is equal to capital N times log base 2, capital N, minus, and we're going to get n sub 1 times log of 2 of n sub 1 plus n sub 2 of log base 2 of n sub 2 plus n sub 3 log base 2 of n sub 3. And it stops there. Since there's only 3 species, we only have to do this 3 times. And this is all going to be divided by capital N. All right, so we have our equation, we have all of our variables, and now we're going to put it all together. So we're going to use our variables to find this. So we know capital N is 2,000, so we're going to say 2,000 times log base 2 of 2,000. So now is when I'm going to start using parentheses. It's going to get a little confusing. So we have that value. And now we're subtracting n sub 1 log base 2 of n sub 1. N sub 1 is 143. So we'll have 143 times log base 2 of 143. Now we're going to do the same thing with n sub 2. N sub 2 is 1,405. So we're going to say 1,405 times log base 2 of 1,405. And now we'll do the same thing with n sub 3, which is 452. We're going to multiply that by log base 2 of 452. And we're going to divide this all by a capital N, which is 2,000. All right, so now we have input all of our information. We know our properties, so we could use properties, but we're going to use our change of base instead. So with using our change of base, we're going to rewrite this, and we're going to get h is equal to 2,000 times the natural log of 2,000 divided by our natural log of 2. So that is how we're going to write our change of base. And that was just our first term, so now moving on to the rest of our terms. We're going to get 143 times the natural log of 143 divided by the natural log of 2. Moving on to our n sub 2, we're going to have 1,405 times the natural log of 1,405 divided by our natural log of 2. Now lastly, with our n sub 3, we're going to have 452 times the natural log of 452 divided by our natural log of 2. And once again, this is all divided by our capital N of 2,000. All right, so we've used our change of base, we've rewritten everything, we have everything in terms of actual real numbers, so we know that we can now calculate this. So I highly suggest going through and calculating our change of bases first. So we'll calculate a natural log of 2,000 divided by the natural log of 2, and we'll calculate our natural log of 143 divided by our natural log of 2, and then natural log of 1,405 divided by a natural log of 2, and then our natural log of 452 divided by the natural log of 2. So let's calculate all of those values, and then we'll come back to this. All right, so if you've calculated this, you should get 2,000 times 10.966. Then we get 143 times 7.16. Then we have 1,405 times 10.456 plus 452 times 8.82. Oh, I crossed out some of those. Divided by 2,000. All right, so now we've simplified just a little bit more. And now we can multiply all of our terms together. And so I invite you to take a moment, multiply all of your terms together. So now we'll just be left with 4 terms to simplify in our numerator. And if you had, we will get 21,932 minus 1,023.88 plus 14,690.68 plus 3,986.64. Oh man, all divided by 2,000. Sorry, I kind of crossed that out. And if we add up all of our terms in our brackets there, we'll end up with 21,932 minus 19,701.2. This is all still being divided by 2,000. We can subtract those values from each other, and we're left with 2,230.8 divided by 2,000. Then we want to calculate this, and what we'll get is 1.1149. All right, so after a lot of calculations, we end up with our Shannon index equaling 1.1149. That would be our index of diversity in our community. So there was a lot of parts to that, but we used a good amount of our theorems and our properties, and there was a lot of calculating. Wasn't that fun? All right, that was such a mouthful, a lot. So now moving on, we have our logarithmic functions. So if a is greater than 0 and a is not equal to 1, so our same kinds of, I'll say properties that we established early on, we have the logarithmic function with base a is defined as f of x is equal to log base a of x. So we're pretty much saying the same thing now, except we're saying f of x instead of y. And f of x and y are pretty much the same thing essentially. It's just that y is one value and f of x means our function of x. Y itself is a function of x, but we have f of x here instead. So now we move on to talk about our exponential functions and our logarithmic functions. So we see that exponential functions are usually seen as f of x is equal to a to the x power. Our domain is always going to be the set of all real numbers, and our range is going to be the set of all positive real numbers. So we see here that our graph, it can go anywhere across our x-axis, and our range will be all positive numbers since our y cannot be negative. Then we see we have a horizontal asymptote and no vertical asymptote, and our horizontal asymptote is our entire x-axis. So we see our exponential functions cannot touch or go past the x-axis. Now we have our logarithmic functions, and we have which is normally seen as f of x is equal to log base a of x. Our domain is going to be the set of all positive real numbers, so x greater than 0. And our range is going to be the set of all real numbers. So our range can be anything, but our domain is positive x values. We see that there is a vertical asymptote, but no horizontal asymptote. There is a vertical asymptote on the y-axis, since we see that our y values cannot be 0 or negative. All right. Oh, sorry. I meant our x values. Our x values cannot be 0 or negative, since that is our set of our domain. Now we're going to use Desmos to see both of these graphs on the same plane, and we're also going to look at y is equal to 10 to the x power and y is equal to log of x. All right, so we're on Desmos, and we see our red line here represents y is equal to the natural log of x. And then we see our blue line here is y is equal to e to the x. Now you may notice they kind of look a little similar. It's just that they are mirrored, like we talked about last time. So, well, they're not mirrored about the x-axis, and they're not mirrored about the y-axis, but they are mirrored around the line y equals x. And we see here that they are totally mirrored, so we know that the natural log of x and e to the x are completely opposites of each other. Now, let's try out y, oop, that was too much, y of 10 to the x and log base x. Now we see that these are mirrors of each other. Once again, over y equals x. So these are mirrors to each other as well. So we know that if we have log base a of x and a to the power of x, those will always mirror each other. And those are because those properties that we talked about earlier. So they're always going to be mirrors of each other, so we know that that is how they are related. They are not completely unrelated terms. They are very much related, and they are just opposites. All right, for our last example here, we have example 8, which is also number 64 in your book. We have the barometric, oh man, that's a tough word, barometric pressure, which is P, is in inches of mercury. And it's related to the height h above sea level in miles by the equation h is equal to -5 times the natural log of P divided by 29.92. The pressure readings given in parts A through C were made by a weather balloon. And we want to know at what heights they were made. So we're trying to find h in this case. And for A through C, we're given our pressures. So let's calculate these. We know our equation is h equal to -5 times the natural log of P divided by 29.92. And in part A, we're given 29.92 divided by 29.92. So we know this is going to simplify to -5 times the natural log of 1. And the natural log of 1 is just going to equal 0, since e to the 0 power is equal to 1. So we know now that this is going to be h is equal to -5 times 0. So it's going to be 0. So for our first reading here, we have that we are 0 miles above sea level. So we're at sea level. Now we'll do the same thing for part B. We have h is equal to -5 times the natural log of 20.05 divided by 29.92. So I invite you to take a moment and calculate this on your own. And if you have, you'll realize that we get h is about 2 miles above sea level. And for part C, we're going to do the same thing. So we'll say -5 times the natural log of 11.92 divided by 29.92. Once again, I invite you to calculate this on your own. And you should have gotten h is about 4.6 miles above sea level. All right. So for part D, we want to graph the function to determine the pressure at h is equal to 3 miles. And we're going to use Desmos for this. All right, so now we're on Desmos, and we have our equation y is equal to, or in our case, it's h is equal to -5 times the natural log of, in this case I wrote x, but it should be p for pressure, divided by 29.92. And if we look at our graph here, we definitely see that there is an exponential decay going on, but we will be going into negative values. But for part D, our question was to use our graph to determine the pressure when our height is 3 miles. And our height represents y in this case. So we'll say y is equal to 3. So we get this second line here, and we see that it's going to cross at this point, and we know that whatever our p or x, since we're using Desmos, is going to have, that will be the pressure. So we scroll over our point there, we see that we get 16.4 and 3. So we know that our height will be at 3 miles above sea level whenever our pressure is 16.42. So you can use Desmos to do something like this, or you can use a graphing calculator if you have one. All right, so we used Desmos to find our answer here, which we got when our height is 3 miles above sea level, our pressure will equal 16.42 inches. All right, so that concludes our section on 4.3. If you have any questions about our lecture or anything in previous lectures, or any questions in general, do not hesitate to email me. Feel free to fill out a question in our anonymous question form as well. So I hope you all have a great rest of your day, and I will see you virtually later.